Means these smooth muscles are always under normal condition remains slightly contracted. Why? So that if necessary, I can dilate the muscles. So if I can dilate the muscle, the diameter will be increased, blood pressure will be reduced, flow will be increased. By dilating, so there is a provision. A provision is kept. If necessary, I can increase the diameter to increase the flow of blood, means to decrease the blood pressure. That's why this provision is made. Okay, so whenever needed, in this condition, if it is needed, it can contract further. If it is needed, it can relax. Thereby, it can control blood pressure. It can, by increasing and decreasing the diameter, these resistance vessels, they are so efficient, minor change in diameter, there may be lot of change in blood pressure. Minor change in diameter, thereby it can influence flow as well as the pressure. Okay, that's why this provision is made. So, under normal condition, all these muscles are under sympathetic tone. When this tone is withdrawn, vasomotor center, it is located in medulla oblongata, VMC, we call it VMC. They are pressure center, depressor centers. When pressure has to be high, pressure has to be lowered. What I have to do? I have to increase the diameter. Blood vessel has to be dilated. So how it will be done? The vasomotor center, it will withdraw the inhibition, withdraw the tone. As a result, the blood vessels will be dilated. Now more blood will be passing. Flow will be increased, blood pressure will be reduced. Thereby it can control. Now blood pressure has increased too much. It is distended. Now what to be done? So I have to reduce it. So what will be done? So these muscles will be contracted and the lumen will be narrowed. Resistance will be increased. Again, blood pressure will rise. Meta-arterioles and peak capillary sphincters. You see what is there? Very important thing. This is artery. From its capillary, one branch is produced. This branch is forming various capillaries. From these capillaries, venules are formed, vein is formed. Okay, and you will find some branch, one of the branch is not forming any capillary. It is directly joining this vein. Directly joining this vein. They are this sort of connection direct connection between artery and vein is called AV shunt, anastomosis. So these are the anastomosis, connection between direct, without formation of capillaries, direct connection between artery and vein. Clear? So what are the need of this sort of veins? What are the functions? What are the functions? It is hot. Now, climate is hot. Why you are feeling hot? Because core temperature is more. Now, outside temperature is also high, so it is very difficult for you to dissipate this excess heat into the environment. Okay, but I have to keep my body temperature fixed at 37 degree centigrade. How you will do it? How we can do it? We have a mechanism of control of body temperature. What is this mechanism? Heat loss and heat gain. When heat loss and heat gain are equal, then body temperature is constant. If body temperature is raised, then what has to be done? Heat loss has to be increased. During this climatic condition, we need to increase the heat loss. How we can increase the heat loss? How we are increasing the heat loss? There are neural process and physical process. What are these physical process? radiation, conduction, convection, evaporation. These are the 4 physical processes. Radiation. Without any medium, heat can pass. Sunlight is coming. It is having heat. Okay. So, this sort of transmission of heat is called radiation. Your body also, your face, your uncovered area, your body surface is also radiating some heat. You will experience it when you will be there in a theater or in a cinema hall. When you come out of the cinema hall, it will be cool outside. Nowadays there is AC. So before that, now it was the whole cinema also were not air conditioned. Too hot inside. All radiating heats accumulated within the room. Okay, this is the radiation. Another is conduction, convection. What is convection? The fan is removing heat from your body. How? By convection. It is moving the air. This air is cooler than your body temperature. This air is coming and touching your surface, taking some heat. Moving, become hot and then move off. So this is convection. And another process is conduction. Very simple. If it is made of iron, you hold it, this part will become heated. So heat is transmitting through this medium. So in this way, I can lose some. If you sit on a steel chair and after some time you move away, then you will find this steel chair is heated. Where from it got the heat? From my body. So what is the mechanism? Conduction and evaporation. I said there is also a neural control. Hypothalamus will increase circulation, blood circulation to the skin. It will increase blood circulation to the skin. What will happen? 2 things will happen. One is there will be more sweat formation. And hypothalamus also stimulate the sweat glands to contract and to secrete more sweat. So now the sweat will be coming to the body surface. Now this is water. So it is having water content. Now this water will be evaporated. So during evaporation, from liquid to gas, it will take some latent heat. It will take some latent heat. And where from it will take this latent heat? From my skin. So my body temperature will be reduced. Okay. So in this way, another way I didn't tell that is the importance of that vessel, AB shunt. And it is enough, its amount is very high in the skin. In cutaneous circulation, you will find lot of AB shunts. Why? My temperature, my core temperature is within my body, core temperature. So before it is liberated into the surrounding, I have to bring this temperature to the surface, to the skin. From, if it comes, more blood comes to the skin, then it will be easy for heat loss. And that to make this easily done, and this AB shunt is made there. So main function is of the AB shunts here, main function is thermoregulation. It participates in thermoregulation. Here, one thing is explained, cross-sectional area, relation of cross-sectional area with velocity. Relation of cross-sectional area of blood vessels with velocity. This is the cross-sectional area, 4.5 cm square in a car, aorta. And it is having velocity of this, 40 centimeter per second, velocity of flow through aorta. So gradually it is reducing. Gradually total cross-sectional area is increasing. Total cross-sectional area is increasing. Why increasing? Because it is producing branches. All are having their own cross-sectional area. Sum total area is increasing. So cross-sectional area in arteries increasing, in arterioles it is increasing, but velocity, when area is increasing, velocity is decreasing. Come on, one plastic pipe, water is passing through, and you are washing your car. But water is coming like this. So what you do? So that water reaches there, you narrow down the tip. Now velocity increases. So narrowing means you are making the flow, increasing the velocity of the flow. So by narrowing the diameter. So if you want to increase the velocity, you have to narrow down the diameter. So here see, total cross-sectional area is increasing. Total cross-sectional area is increasing, as a result, velocity is decreasing. And here it is what? Again, the venous. Again, cross-sectional area rising. Cross-sectional area, again, what is happening? The area rising and velocity. So this is the cross-sectional area, and this is the velocity. Again, velocity is rising because of increase in cross-sectional area in the veins. The vessels are of 5 types. Oh, this is the composition. 5 types. What are these? Windkessel vessels. I already explained it. Another is resistance vessels. I also told it. Exchange vessels. These are what? Arterioles. These are exchange vessels are arterioles. And capillaries. Here no blood vessels, no smooth vessels are there, only endothelial cells. Only endothelial cells. One single layer of endothelium is there in the capillaries. Okay, no muscle layer, no elastic layer, only smooth muscles. Now these smooth muscles, now these endothelial cells are nothing but squamous epithelium. Squamous epithelium, single layer, one, continuously they are arranged. Okay, and they are flat. And this endothelial cell, inner surface is very smooth. Why inner surface is smooth? Because through the blood is passing through the lumen, and in the blood, what are there? Different type of blood cells. One is platelets. The platelets are very fragile. If they find any rough surface, they will be broken down and there will be coagulation of blood. There will be blood clotting. To prevent that, it should be smooth. Okay. So now this capillaries, only what is there? Endothelium is there. Now we'll see capillaries are of 3 types. Capillaries are of 3 types. What are these? These exchange vessels. These exchange vessels are of 3 types. What are these? Capillary endothelium, lined on a basement membrane. This is the basement membrane, capillary endothelium. Okay? So this is the wall, here the blood is flowing. Now there should be exchange through this wall, exchange between cell, body tissues and the blood. So in between, it is blood, here is the, it is the, here it is the blood, it is the wall. Now the contents of the blood has to come to, here the tissue cells. So it has to pass through this endothelium. How it will pass? These cells are having pores. You can see these pores, but the cells are tightly packed. These cells are having pores. So the blood that has to be diffused. So they will first enter into this, and they are also having pores. From there it will enter into the tissue space, then into the tissues. That's why they are called continuous or non-fenestrated. These endothelial cells are continuous, no gap in between, no fenestration. Only the cells are having in both luminal surface and basal surface they are having, or basolateral surface they will be having pores. Through these pores, exchange will be done. And second type of capillaries are this type, fenestrated. This is one cell, this is one cell. In between, there are small gaps. These are called fenestration. So some capillaries are fenestrated. And another type of capillaries are there. They are one epithelial cell, endothelial cell is here, another endothelial. In between there is a gap, long gap. And this sort of capillaries we will get in sinusoids. These are actually sinusoids. In liver, what is there? If you get the cross-section of the liver, histological structure, then you will find the lobules. You have seen the slides. You are there in hepatic lobules, hexagonal shaped lobules. At the center, there is central vein, and from the cell vein, radiating columns of hepatocytes are there. In between radiating columns of hepatocyte, there is a space. This is called sinusoids. These sinusoids are made up of these cells. This type of capillary. This type of capillaries. They are also present in brain. Okay. Another thing. Just tell me, what is your idea? We are having blood, certain amount of blood. What is the quantity of this blood? 1/7 of your body weight. What is your body weight? In some books it is written as 1/10, some books 1/9. So suppose manlo it is 1/10, 1/8. Your body weight is 50 kg. 1/8 of this, 8 भागेर 1 भाग. 80 kg, divide 80 kg by 8. 8 liter. No, it is 1/10. 80, 1/8. 80 kg divided by 8. How much comes? 10. That means if you are 80 kg body weight, you will be having 8 liters of blood. If you are having 50 kg weight, suppose your weight is not even 50 kg, how much you will be having? Blood? 50 kg divided by, your body 50 kg, divide it by 7. 4.9. 5 liters. Actually, we are having roughly 5 liters of blood. Actually, how much? 5 to 6 liters of blood we are having. And every minute, this blood is circulating throughout my body. How much blood is circulating throughout my body in 1 minute? Okay. What is cardiac output? The amount of blood ejected into the circulation in 1 minute. In 1 beat, you eject 70 ml. In 70 beats, how much? Every beat 70 ml. In 1 minute, you beating 70 times. So in 70 times, how much blood you are ejecting? 70 into 70, 4.9 means 5 liter. Every minute you are pumping 5 liters of blood. Now this 5 liters of blood at a time. Now at this instant, my 5 liters of blood is distributed throughout my body. Now tell me whether these 5 liters of blood, how these are distributed? Whether most of the blood is retained within the artery system or in the venous system. Why you are telling this in venous system?
Veins act as,
you are correct. Now explain.
Veins act as reservoirs because they are distensible but they do not contract elastically.
Right, very right. That's why they are called capacitance vessels. They can accommodate they can accommodate large amount of blood. When somebody is having injury, and initially blood will come from the venous system, those blood will be coming out. Okay, now the venous system, so the why this blood will be coming out? So these are some sort of reserve blood. So that can be, I can spare it, but immediately, but some amount of blood was wasted or lost from the arterial system also. But in the arterial system must have adequate amount of blood. So that's why then these veins will be contracting, rest of the some amount of blood will be entering into the arterial system so that blood volume is maintained. Arterial system can remain in patent state. They are having something there to pass, no? So blood has to be there. So they now this from the capacitance vessel through contraction, this will be coming to the arterial system. So now they will be circulated as an acute effect, as an acute measure. See. So that's why these veins are called capacitance vessel. Is that clear? Okay, fine. Next. See how my 5 liters of blood, 6 liters of blood distributed. In big veins, 39% of blood is accommodated there. That's why they are called capacitance vessels. And in the small veins, 25%. So together in venous system, how much is a C? Most of the blood remains in venous system. And in the arterial system, aorta, small arteries, how much is this? Only this much. And in the lung and heart, only this much. Okay? Now you got the idea? Always, every time, most of the blood is retained in your venous system. In veins, large vein, small veins, venules. Now tell me, one by one. From aorta, if you proceed toward the cell through the blood vessels, what will happen to the pressure? Gradually, they're increasing or decreasing? What we have seen in the chart, gradually decreasing. Gradually decreasing. And in the capillaries, what is the pressure? This pressure is called hydrostatic pressure, 25 only. Why there is no diastolic pressure in the capillaries? Only systolic. Who is creating this? The elastic layer. This is in the arterial system. We see during systole expanded, during diastole the vessels have. If these elastic fibers are not there in the peripheral region, then who will do it? Now nobody is there. Only because of systole they will be flowing. And there will be mean pressure. Because of mean pressure, blood will be flowing. Okay? So this is one thing you came to know. Another thing, surface area, total cross-sectional area is gradually increasing. As a result, what happens to total resistance? Falling or resistance যদি বাড়ে, total cross-sectional area যদি বাড়ে, resistance কি বাড়বে না কমবে? কমবে, তাহলে কি পেরিফেরিতে প্রেসার বাড়বে? কমবে, প্রেসার কমবে, but flow will remain same. এটা কেন করা হলো? Gradually velocity কমে যাচ্ছে। Velocity আমি কমিয়ে দিয়েছি by increasing the number of branches. এটা করে আমার বেনিফিটটা কি হলো? Ultimately blood is coming to the cells. Why? To deliver something to the cells. আর ডেলিভারি টাইমটা তো দিতে হবে, না যাবে সঙ্গে সঙ্গে চলে যাব। ভেলোসিটি বেশি হলে তো আমি এক্সচেঞ্জ করার সময় পাবো না তো, এটা তো ফাস্ট চলে যাবে, ভেলোসিটি ভেরি হাই। তো আমার যদি ভেলোসিটি আমি কমিয়ে দিই, নাও উইল গেট দ্য টাইম অফ এক্সচেঞ্জ। দ্যাটস ওয়াই আই হ্যাভ রিডিউসড দ্য ভেলোসিটি। হাউ আই হ্যাভ রিডিউসড দ্য ভেলোসিটি? By increasing the total cross-sectional area. Flow is maintained, adequate flow is there, but only thing, velocity I reduced by increasing the total cross-sectional area. So that the tissues can get enough time, adequate time for exchange purposes because of reduction in velocity. Can anybody tell me what is this? These ring-like structures? Precapillary sphincters. What is their function? They are under neural control. They are under neural control. What is their function? You have to remember this thing forever. Sphincter. When they are stimulated, sphincter is closed. So no blood can pass through it. Capillaries become dormant, no blood is through. When the sphincters dilate, blood will be passing through this. I said, under normal condition, we have lot of capillaries, but all capillaries are not active. They remain dormant. If necessary, I have started working, exercising. My energy demand, tissue demand for oxygen, for nutrients has increased. So, how it will be supplied? It has increased. So, I have additional capillaries through that. Now, these capillaries will open. They will become now patent. So, this now additional blood will be coming and will be supplying the tissues. And this is, who is controlling this? These sphincters. Who is controlling these sphincters? Sympathetic nervous system. Okay, this part. Blood flow. Blood flow, important part. Blood flows through the blood vessels. If you place a stethoscope and try to hear whether any sound is there, will you get any sound on the? Suppose this is the blood vessel, one artery is going this way. So you keep the diaphragm on this and try to hear whether there is any sound or not. Will you hear any sound? You will not hear any sound. But sometimes you can hear sound. When blood flow, two types. One is laminar, another is turbulent. Laminar flow means this is the blood vessels. So blood or water, whatever any fluid is passing through it. While passing, it forms several layers. Outer layer, then inner layer, multiple layers. And the fluid is parabolic. The central part is ahead of all the layers. Central layer is ahead of all the layers while flowing. But the outermost layer, they are lagging behind. Why they are lagging behind? Suppose this is the outermost layer, this is the inner layer, endothelium. Now this is the outermost layer of fluid. So where this layer will be passing through this is stationary. This wall is stationary. It is not moving, but this layer is moving. So while it will passing, this layer and this layer, they will undergo friction. Friction is a resistance. Because of this resistance, their velocity will be reduced. Their flow will be reduced. But next to this layer, it will find the first layer of the fluid is moving to some extent. But earlier, it was not moving. Here it is moving. And the third layer is also moving. But second layer is relatively less. So here friction will be less. As a result, second layer will be little bit ahead. Third layer, inner third layer, they will be ahead of that. And the picture is like this. It is facing more friction. Here this is moving, this layer is also moving, but it is having less speed, it is more speed. As a result, its speed will be higher than this, and the central part will be having the high speed. It is having the minimum friction. As a result, this will go. So this sort of flow is called laminar flow. This sort of flow in layers, they are flowing, and the central layer, this layer form a parabolic form to go ahead. Okay, so this sort of, and they are very smooth, not noisy. It will not produce any noise. That's why blood is flowing through the arteries, through the veins. They are laminar flow. That's why no noise, no sound is made. The parabolic nature. This is the turbulent flow. What happens here? These layers, their movement is haphazard. Every component of this layer are colliding with each other. So as a result, what is happening? So there will be formation of noise, creation of noise, and this noise can be heard. This noise means sound, it will produce sound. This sound you can hear using a stethoscope. And why it happens? When velocity of blood flow is increased too much. How? This is one blood vessel. Suddenly you have, here it is having this much diameter, flowing, fine, laminar flow. But when it is, some part is narrowed, velocity will be increased. Since it is narrowed, now because of increase in velocity, here it will produce turbulence. Now if you place a stethoscope there, you will be hearing this sound. This sound is called murmur. Bruit. Murmur or bruit. Whenever you hear this sound, murmur, that means turbulence is going on. The murmur is because of turbulence. Now it can happen where? In the heart. It can happen in the blood vessel because of atherosclerosis in the blood vessels. In the atherosclerosis, what happens in atherosclerosis? Blood vessels. Carotid artery, stenosis. This part, this is the normal artery. Here it is narrowed. Here it is narrowed. This is the plaque, formation of plaque, atherosclerotic plaque. Inner layer is thickened. So lumen is narrowed. As a result, while blood passing through this narrowed, velocity is increasing. Here velocity is increased too much, so it will produce turbulence here. So since there is turbulence, so if you keep the stethoscope, you will be hearing. So if you find any noise there, that means what is there? There is a complication. What is this complication? Carotid artery stenosis. So if you find any noise in the peripheral blood vessel, that is, there is stenosis. And in the heart, the valves can undergo stenosis. The valves, all the valves can be stenosed. See, this is the result. This is normal valve, semilunar, tricuspid valve. Semilunar valves. Okay, this is open, this is closed. And you opening, fine, nicely opening and closing nicely. But here you see, it is stenosed. It has become, by deposition of calcium, they become heavier and shorter. Heavier and shorter. As a result, when they are opening, incompletely opening. So see, here diameter is, open diameter is more. Here open diameter is less. Lumen is narrowed. As a result, when blood will be passing, either this direction or that direction, it will produce sound. And you will hear murmur. in the heart also. Depending on the location of the sound, you can say which valve is affected. Either it is aortic valve or in the pulmonary. There are, when I will be explaining the different heart sound murmur, different types of it may murmur you can hear during systole, you can hear during diastole, you can hear continuously, because the wall of the blood, wall of the heart, atrioventricular wall, or within the atrium there is one IS, intra-atrial septum, intraventricular septum, they can be perforated. So if it is perforated, so every time blood through a narrow lumen blood will be passing, so it will produce turbulence and you will be hearing the sound continuously. Okay, now see, during systole, in this case, take this case. Semilunar valves, okay, we know second heart sound is produced because of closure of this valve. So in this valve will be closing, second heart will be sound, and this sound will be continued. Why? Because even these are closed, some gap is there, fully not closed. So some blood will be passing, re-entering from aorta into the ventricle. Regurgitation will be there, backflow will be there, and it will cause, since it is very narrow, it will produce turbulence and it will create sound. So this is, see, during diastole also you can see the noise. This is diastolic murmur. During systole you can hear, if it is not properly opened. See, in this case it is not properly opened, it is narrow. So when narrow lumen, through when blood will be passing through this, so what will be there? There will be turbulence and we will be hearing the turbulence. Very important for you. So by stethoscope you have to identify whether there is any valvular disease or not. What type of murmur it is. By classifying them, depending on the type, this intensity, you can say where the stenosis is, which valve is affected. Okay, only because of turbulence. So turbulence flow is important in diagnosing heart diseases, vascular diseases. Whether blood flow will make turbulence or not, whether blood flow will be turbulent or not, you can determine it using a number, calculating a number. This number is called Reynolds number. What is this number? Reynolds number. How you can calculate it? Using this formula. This is Reynolds number. It is equal to density of the fluid, and it is the velocity of the fluid, and it is the diameter of the blood vessels. Narrow the diameter, more the chances of increasing Reynolds number. Joto na diameter ta less hobe, less the diameter, more will be the Reynolds number, more the chances of turbulence. More the velocity, more the chances of increasing the chances of increasing this value. Okay, and it is what? It is the viscosity. Inverse related. Means what? If viscosity increases, what will happen? Reynolds number. Viscosity decreased, what will happen to Reynolds number? Inverse related. The relation of Reynolds number with viscosity is inverse. To increase in viscosity, what will happen? Reynolds number will increase or decrease? Decrease. So no turbulence. Thick viscosity increase. When thick fluid has least chance of making turbulence. isn't it? Common sense. You apply the common sense. And the lighter fluid, has the chances of, so less the viscosity, more will be the Reynolds number. So Reynolds number depends on what? Density of the fluid, diameter of the blood vessels, directly proportional, and velocity of the fluid. Okay, and inversely related to the viscosity. And if the number is more than 2000, there is a chance of turbulence. The flow may cause turbulence. So how can you determine whether blood flow will be turbulent or laminar? Less than 2000, Reynolds number less than 2000, laminar, more than 2000, turbulent. Again, what are the factors? Directly related to density, velocity, and diameter of the blood. Density of what? Density of the blood, and velocity of the blood fluid, and diameter of the pipe, that is blood vessels, and the viscosity. With viscosity, it is inversely related. Another important, we have learned there are some laws and principles. One of the law is Poiseuille's law. Poiseuille's law. Okay? This law actually explains the relation of some factors with flow of blood. Flow of blood means Q. Q means flow of blood. And with this Q, what are the other factors that are affecting Q, that is flow of blood? What are the other factors? One is the radius of the diameter, radius of the vessel. One of them is radius of this vessel. And second one is pressure change. Blood will be, any fluid will be passing from here to there, from this point to this point. So what is the pressure difference? That is the delta P. So if the delta P is high, pressure change is high, flow will be more directly related, we can see. And the radius, more the radius, more will be the flow. Less the radius, less will be the flow. And power 4 means minor change of this can affect much change in flow. Only little bit change in diameter, in radius, you can change much change in. So the nervous system will make certain increase or decrease, and it will affect the flow of blood. And what is this part? This is what? Viscosity. And this is the length of the vessel. So this is the relation. So what are the factors here affecting Poiseuille's law? Actually, while the blood is having laminar flow, Poiseuille's equation describes how flow rate is affected by what? Vessel radius, length, viscosity, and pressure. Actually, it is the relationship between flow with pressure change, with viscosity, with diameter, and with length or diameter of the vessels, length of the vessels. So this relation. Now, one thing we know from this equation, one thing can be derived. What is the peripheral resistance, role of peripheral resistance? From this equation, we can determine the peripheral, how much the peripheral resistance is, and what are the factors affecting peripheral resistance. We know flow is equal to pressure change divided by resistance. That means flow equals to pressure change by resistance. Remember this. Pressure change divided by resistance. Okay, these are equal. That means if pressure is increased, flow will be also increased. And if resistance is increased, flow will be decreased. If resistance is decreased, flow will be increased. So this is the relation between resistance, delta P, and pressure change, and flow. Now I am to replace this. This is the Poiseuille's equation. This is the Poiseuille equation. Now I am to replace this with this. Delta P by R. Okay, open it. Open your notebook. First write the Q is equal to delta pi R or pi R to the power 4 delta P by 8 NL. So now I want to replace Q. I am to replace Q with this delta, because Q is equal to this by this. So what I will delta P, you write here delta P by R. Replace Q with delta P by R. Okay, and rest of the part is same, equals to rest as same word pi R to the power 4 delta P by 8 NL. Now simplify it. I want R. What will be the R? Then you will find how R is affected. Okay, ওটা বেরিয়েছে নিচের এটা? R equal to 8 NL by pi R4. Now can you tell me what is the relation of R with viscosity? What is the relation of diameter with resistance? What is the relation of length with resistance? What is this N? What is this called? Eta. Eta means viscosity. So what is the relation of viscosity with R? Higher the viscosity, higher will be the resistance. Lower the viscosity, lower will be the resistance. Higher the length of the tube, higher will be the resistance. Okay, and higher the diameter, or radius, what will be? Resistance will be less. Inverse relation is less. So now you can infer easily. In periphery, what is the resistance? Who will be creating resistance? They are the factors. These are the factors, they can create resistance. And these factors can affect my blood flow. There are two other Bernoulli's principle and Laplace equation. It is for your self-learning. You will learn it by yourself. Dynamics. Hemodynamics means, hemo means blood, and dynamics means power, energy. During circulation, blood circulation, so many things happens, so many physical changes happen. So we can see, we will be noticing during the circulation of blood through the vessels, this circulation will obey certain principles, laws, physical principles. How they are related to circulation, that will be explained. And these are important also. Moreover, all these principles are related to different aspects. What are these? These are the laws. These are involved in physical laws involved in circulation, blood circulation, while blood circulates through the vessels. And the hemodynamics will involve these physical factors. What are these? These are peripheral resistance. We will understand what is peripheral resistance, blood flow, pressure gradient, energy, vessel, its diameter or cross-sectional area, blood velocity, forces, blood viscosity. Okay, all these will affect our blood circulation, flow of blood, while flowing, it will be facing resistance while flowing towards the periphery, means towards the capillaries, it will face various resistances. What are these resistances? Okay, so this we will be discussing. Before that, we'll just know, after aorta is originated from heart, it will produce several branches. So aorta is giving off several branches. What are these? Large artery. Again, the large arteries will be dividing into smaller arteries. These smaller arteries will produce lot of even smaller branches. These are called arterioles. Now these arterioles again will produce capillaries. Again, these capillaries will be joining together to form venule. Now the various venule will be joining together to form vein. Now the lot of veins will be combining together to form either superior vena cava or inferior vena cava. Okay, so this before we discuss the various aspects, we will be highlighting some aspects of structures of the blood vessels. So I think you have already gathered some knowledge in anatomy class. I am not sure. So structures of blood vessels. Okay, what is the structures of this aorta, arteries, arterioles, and capillaries, venules. Okay, so let us see. Except arteriole, capillaries. Before that, means starting from aorta, large arteries, small arteries, small arterioles, they will be having 3 layers. What are these 3 layers? The wall will be having 3 layers. Tunica, adventitia or tunica externa, and in between and the middle part, tunica media, and the inner part, fine, tunica intima. Okay, arteries, mainly as it gives up branches at aorta. See how diameter is there, diameter is changing. Initially, what is the diameter? You have to remember this thing. See, gradually diameter is decreasing. Aorta, it's giving up large arteries, diameter is reducing. Smaller arteries, even further it is reducing. In arteriole, it is this much. And in the capillary, it is this. And in the venule, it is this. In the vein, it is this. And in the vena cava, it is this. So now one thing you just try to remember. In aorta, what is the diameter? 25. The diameter is having 25. Okay. Now, it will giving branches. I am coming into another, this one. Aorta is having cross-sectional area. So, suppose this is the diameter. So, this is the cross-sectional area. What is the cross-sectional area? 4.5 centimeters square. So, what will be? It will be giving off branches. Every branch will be having smaller cross-sectional area. Now, if you add the cross-sectional area of all the branches, what will happen? The summated amount will be more than the aorta. Aorta is having 44.5 centimeters, but when you add the smaller artery, diameter of all small arteries, then every small artery is having diameter of, total diameter will be 72 centimeters square. It is increasing. Total diameter. Aorta, it is giving us several branches. So you add all the cross-sectional area, and how much it will be? 76 centimeters. And how many times of aorta? 16 times of aorta. Okay. Again, in the arterioles, it is further increased. Arteries are smaller. It is further increased. Cross-sectional area is further increased to 4,000 centimeters square. and in the capillaries, that too at rest. So one point is given, at rest only 25% capillaries are open. And while we do exercise, some capillaries remain dormant. No blood flows through those arteries. They remain dormant. But when we do exercise, they open up. And before that, how they work, I will be discussing. And again you see cross-sectional area is increasing. Again, cross-sectional area is increasing. And in the venule, it is 4,000, less than this. And in the small veins, it is 80 centimeters square. And in IVC and SVC, it is 18 centimeters square. Why these changes have been made? Why? Gradually, cross-sectional area is changed. Now, one thing you see, here velocity was 40. And gradually, what is happening? 40 centimeter, 1.4 centimeter, 0.5 centimeter, 0.3 centimeter, it is reducing. Velocity is reduced. Okay? Why velocity is reduced? We know if a tube gradually becomes narrower, single tube becomes narrower, what will happen? Velocity will be increased or decreasing? Velocity will be increased. Here see, the arteries, all arteries gradually their diameter is decreasing. But velocity, instead of increasing, it is decreasing. Did you notice that? Velocity is decreasing. Why velocity is decreasing? Because it is not a single one. Multiple branches are there. As a result, cross-sectional area is increasing. So all the blood is distributed to all these branches. As a result, the velocity is also decreased. At the origin of a river, see the velocity of flow. And see at the tributaries, see, the velocity will be much less. Because it has produced several branches. Okay. So this is one thing, one point you have to remember. Now one thing, you tell me, at the beginning of the arterial system, vascular system, and the aorta, what is the blood pressure would be there? 120 by 80. Okay. Now if you proceed gradually towards the capillaries, what will be their pressure? It is gradually decreasing, no? Diameter, or the pressure will be increasing or decreasing? Decrease. Why decrease? Why it will decrease? Okay, you are right. See how pressure is changing. Distribution of blood-brain vascular system. What happens to the pressure? In aorta, it is 120 by 70. In arterioles, it is reduced to 60. Where is the diastolic pressure? Where is the diastolic pressure? Why only 60? There is no diastolic pressure. Even after that, arterioles 40, no diastolic pressure. Capillaries 25, no diastolic pressure. Venule and after 10, 2, this has no diastolic pressure. Why? The answer. In left ventricle, see, during systole pressure is 120. And when it is undergoing diastole, at the end of the diastole, pressure is 0. Okay? When this blood enters into the aorta, systolic pressure is 120 and diastolic pressure is 80. When the blood pressure is blood is passing to small arteries, what is this? Systolic and this is diastolic. What is the difference between systole and diastole? What is this called? Systolic pressure minus diastolic pressure. What is this difference called? This is called pulse pressure. What is this called? Pulse pressure. See, here in aorta, here the pulse pressure is this, and here pulse pressure is reducing, and here no diastolic. Means single, no biphasic flow. No systole, no only singular. There is only one pressure. Why? The pressure here now is laminar. Before also it was laminar. It was now monophasic. No systole, no only systole. Systolic pressure is coming. No diastole. No diastolic. Systole, diastole, no systole. Again, you see here when blood is coming, only one pressure is there. This is the actually mean pressure. What is mean pressure? How can you determine the mean pressure? How can you determine the mean pressure? What is mean pressure? Diastolic pressure plus 1/3 of pulse pressure. Diastolic pressure plus 1/3 of pulse pressure. My blood pressure is 120. My blood pressure is 120 by 80 millimeter of mercury. What is the pulse pressure? Difference 40 millimeter of mercury. What will be the mean pressure? Diastolic pressure means 80 plus 1/3 of pulse pressure. 1/3 of 40. What is this? How much is this? 14 or 18? So that will be, when you added this with that, it will be my pulse pressure. Okay. No, sorry, mean pressure. So this is the mean pressure. No phase. No, there will not be any fluctuation. Here you are getting fluctuation. Systole, diastole, this pulsation you are getting because it is an artery. When you will be proceeding towards the arteriole, you won't get. No pulse. Means flow, there is only one flow is there, it is there. Okay? Now I am coming into the composition of wall. The first tunica adventitia, it is made up of what? What is the composition of tunica adventitia? Yes, collagen fiber and elastic fiber. What is the purpose of elastic fiber here? It will be having elasticity. If you apply pressure, it will be distended. Again, it will try to come to the original position, creating a pressure. It will again, because I have distorted it, now it will be coming to its original position. It will creating a pressure. Why you get pulsation? Why you get pulsation? See, one thing you answer. During systole, blood is entering from ventricle into the aorta. Then valve closes. No blood is entering into the aorta. Then what will happen? The flow of blood will be ceased for that period. Since no blood is entering, so there will not be any flow through the aorta. What will happen? Or there will be flow. Blood has entered from ventricle into the aorta. Okay, during systole. Now during diastole, semilunar valve is closed. No blood is entering. Now what will happen? Since no blood is entering, whether any blood will be flowing to the artery, through the arteries? What is the answer? So systole, blood will be flowing. During diastole, no blood is entering, so there will not be any flow. This is your conception. No. Even during diastole, blood is flowing through the artery. How it happens? How it happens? From ventricle contracted, blood entered. Since its wall is elastic in nature, so it will be expanding. It has expanded, it has accumulated all the stroke volume, all the blood of stroke volume. Stroke volume means stroke volume, the amount of blood ejected by each ventricle during each contraction. One contraction, one ventricle, another ventricle. So every ventricle is ejecting certain amount of blood in their corresponding blood vessels. This amount of blood is called stroke volume. Okay, and its amount is normally 70 ml. How much? 70 ml. Okay, ventricle can contain how much blood? 130 ml. During diastole, it will accumulate 130 ml of blood. But it will be ejected only 70 ml. So, end diastolic volume, what is the end diastolic volume of the ventricle? 130. End diastole, after diastole, what is the volume? When it is fully distended, each ventricle will be containing certain amount of blood and its amount is 130 ml under normal condition. Now, during contraction, out of this 130 ml, only 70 ml will be ejected into the, either in the pulmonary artery and or into the aorta. So, what percentage of blood is ejected? What percentage? 70 out of 130. What is the percentage? 70 divided by 130 into 100. This is called ejection fraction. In echocardiography report, you will get EF, ejection fraction. With this ejection fraction, you can assess how strong is your heart. Whether your heart is effectively ejecting the blood into the circulation. If there is peripheral circulation is increased, it will not be able to eject this mass amount, it will be gradually decreasing. When ejection fraction will be gradually decreasing, it means in the periphery there is lot of resistance. Now, because the resistance is more, the ventricle is unable to eject the blood because their force is more. If it has to deliver all the 70 ml, then it has to generate lot of pressure, lot of contracting pressure, lot of force. But heart is not having that much of force. So as a result, what will happen? The ejection fraction will be reduced and always the amount of retained blood will be gradually increasing day by day. And heart will be proceeding towards failure. Main function to pump out blood, but it is not unable to pump out blood in the circulation gradually. So it will undergo failure. Okay. So what happens? It is ventricle has ejected some amount of blood during systole. So now this aorta, it is distended. Because its wall is elastic in nature. It is having thick elastic layer. Outer layer is very thick and it is having more collagen. And as a result, this will be thickened. So all the 70 ml of blood is actually accommodated here. Okay. Now it is going to diastole. As a result, valve is closed. Cellular blood is closed. No blood is entering. Now what will happen? Because of elasticity, it will be contracting. It will be coming to its original. So this blood, now where this blood will go? Where this blood will go? It cannot re-enter into the ventricle. So it will, see, it is happening when? During diastole. During systole, blood is going. But during diastole also, blood is flowing. That is the cause. Okay? So that is for this reason, we will find during systole blood is flowing and during diastole also blood is flowing through the arteries. Is that clear? Fine. What is this? This aorta is called Wind-Kessel effect. This is called the Wind-Kessel effect. Because of the Wind-Kessel effect, blood flows during diastole also because of wind castle. What is wind castle? It is a German word. German word. Wind castle means elastic reservoir. So this aorta is acting as elastic reservoir. Okay. So that's why it is termed as wind castle artery, wind castle vessel. After artery, main artery aorta, we will get arteries, smaller arteries, and these arteries are having thick middle layer. Having thick middle layer. One thing we understood. What is the effect? What is the function of the aorta? Wind castle effect. During diastole, to push the blood in forward direction. This is the main function. And what is the main function of the next part? Arteries. What is the main function of the next part? Next part, the function is, its wall is, middle part is highly thick, means these are made up of muscles. And these muscles can contract and relax, made up of smooth muscles. And these smooth muscles are of two types. One is unitary smooth muscle, another is mouth unit. Okay, so all this type of smooth muscle will be there. Here in the artery, smaller artery or bigger artery, there also what type of, all will be contracting. Whenever they will come, all will be contracting together. Means all are unitary. All are unitary. Okay, so when they are contracted, some are arranged spirally, some are arranged circularly. When they will be contracting, the lumen will be narrowed. Lumen will be narrowed. As a result, what will happen? Resistance will be developed. Resistance to blood flow. So there will be increase in blood pressure. There will be increase in blood pressure. So by increasing, by contracting and relaxing, you can increase or decrease the resistance. Who can do this? These vessels. What are these? After aorta, the branches of artery, this aorta, they will be having this property. They are having thick layer of muscle cord. They will be they are able to contract and relax. Thereby it can increase or decrease the resistance. That's why they are called resistance vessels. Okay, and they are under the control of the central nervous system. That too under sympathetic nervous system. Under sympathetic nervous system. There is no parasympathetic supply. Okay, now these blood vessels, these smooth muscles are always under sympathetic tone. Always under sympathetic tone.